Hey guys, welcome back. Alright, so today we're going to be doing our final exam review over the topic of differentiation. Now, we're not going to be going full speed into differentiation. That would take way too much time to do in a review video. So if you want to get the full detail on differentiation and its theory, you need to go watch those videos from chapter 3, those lecture notes, those homeworks, everything that goes into much more detail about the definition of the derivative, what it is, its behavior, tangent lines, things of that nature. In this review, all we're going to do is go over taking derivatives. That's it. Just going to practice doing all the different rules that we have for differentiation. Product rule, quotient rule, chain rule, trig, exponential, logarithm, things like that. So I just got 12 examples for you, and we're just going to march through these examples, and we're just going to go over in detail the techniques that you would use to differentiate all of these functions. All right. Now, this is not necessarily the only way derivatives will appear on your final exam. You might be asked questions about finding horizontal tangent lines, extrema, things like that. So these final exam reviews are not necessarily comprehensive. They are not necessarily all-encompassing. So while this review does highlight a lot of the most important stuff to hit for differentiation, it is not everything. So do not solely rely on these final exam review videos to study for the exam. Use everything at your disposal. All right? Well, that's enough of that. So let's just go ahead and get into these derivatives examples, shall we? The way it's going to work is just like the other videos. I'll pause the video here, I'll write out the problem, and then we will go from there. All right? All right, first problem up, it is the function f of x is equal to x cubed plus 2x squared plus 5x minus 9, which is a standard polynomial, and we want to find the derivative of f prime. So here's what we do. We get the derivative with respect to x of f of x is equal to the derivative with respect to x of x cubed plus 2x squared plus 5x minus 9. But because these are all added to each other, there's no products or quotients or anything like that, we get that the derivative of the sum is just the sum of the derivatives. So we can pass the derivative notation to each term. So instead of taking the derivative of the whole thing in one go, we pass the derivative to each individual term, and then we take this derivative term by term. So just took the derivative and we pass it to each term, just like that. We just pass it each term. Now we're going to take the derivative of each one. So what's first? What is the derivative of x cubed? Well, that's just 3x squared. How do I know that? It's the derivative rule with a derivative. It's the power rule for differentiation. You take the exponent, pull it down in front, and then subtract 1 from the exponent. So it becomes 3x squared. And now we can repeat this process again for this one. So we get 2 times 2 times x to the 2 minus 1. So we have our 2 out in front. We pull down our exponent down in front, subtract 1 from the exponent, plus, now the derivative of 5x. This is we're going to want to use the derivative of x rule. Basically, when you just have the derivative of x, it goes away, and you're just left with whatever constant you have. So that's equal to plus 5, and then plus, now what's the derivative of a constant? The derivative of constant is a 0 every time, no matter what. The derivative of constant is 0. So that is plus 0, and this is equal to 3x squared plus 4x plus 5. And that is how we get our answer. Just pass the derivative each term, take the derivative term by term, pull down those exponents, and there you go. That's how we take the derivative of these polynomials. All right, now let's look at this next problem. F of x is equal to arctan of x plus 7. Now this we wish to differentiate. So we want to find ddx of f of x. Well, that's equal to ddx of arctan of x plus 7. And then we're just going to take the derivative of this term by term. Now, The only way to get the derivative of arctan is to remember what the derivative of arctan is, or build the representation of triangles, use the idea of what arctan is, come up with the ratio of sides, differentiate that using implicit differentiation, and come up with your answer. But that sounds like a lot of work. I think at this point it would just be easier to memorize the formula, personally. So I'm going to take the derivative term by term. First what we need to do is take the derivative of arctan. So this is equal to the derivative of arctan of x. But what is the derivative of arctan of x? That is just 1 over 1 plus x squared. And then we have to do the same thing with the next part. We have to take the derivative of x. But what is the derivative of x? Well, that's just plus 1, right? Derivative of x is 1. And then now, finally, we pass this derivative to the 7. What's the derivative of 7? What's the derivative of constant? So that is just equal to 0. So our derivative is 1 over 1 plus x squared plus 1. We just recognize the derivative of x, the derivative of constant, and the derivative of arctan of x. And then we use the linearity of the derivative to take this derivative term by term. All right? So nothing too complicated about this one except remembering what the derivative of arctan is. All right. Now let's look at the next problem, number 3. Let's take the derivative of f of x is equal to cosine of x plus sine of x. So we want to find d dx of f of x, right? Well, that's just equal to the derivative of each term. So that's equal to the derivative of cosine of x plus the derivative of sine of x, right? Now, to do this one, the only way you can do this is if you have your trig formulas memorized. There is no other way around it. You have to have those trig formulas memorized. So, we need to take the derivative of cosine of x. Well, that's just negative sine of x. Plus the derivative of sine of x. Well, that's just cosine of x. And then because I don't like leading with negatives, this is equal to cosine of x minus sine of x. So the derivative of cosine becomes negative sine, the derivative of sine becomes cosine, and then because I do not like having this negative right here out in front, I swap the terms. So this derivative is equal to cosine of x minus sine of x. And that's really all there is to that problem. All right, now consider this function. F of x is equal to sine of 2x plus 2 cosine of x. And we want to find the derivative with respect to x of f of x. Well, due to linearity again, we know that's equal to the derivative of each term individually. So we just pass the derivative through. And then we just take the derivative term by term. Now notice, here, this isn't just sine of x, it's sine of 2x. So we cannot just use the standard trig rule here and call it a day. We have to use the chain rule. So the derivative of sine of 2x is equal to the derivative of the outside, leave the inside alone, times the derivative of the inside. As such, this derivative is equal to cosine of 2x, that's the derivative of the outside, leave the inside alone, times the derivative of the inside, which is just the derivative of 2x. And now plus this derivative. Now, we have this 2 out in front, we can just ignore him. That's a constant. We can pull him out in front and ignore him. So this is just equal to the derivative of 2 cosine of x, which is also just equal to 2 times the derivative of cosine of x. And now this is equal to cosine of 2x because we're not doing anything with that guy, times the derivative of 2x. But what's the derivative of 2x? Well, it's just 2. And then over here we have plus 2 times the derivative of cosine of x. But what is the derivative of cosine of x? Well, that's just negative sine of x. And then by simplifying, we get this as 2 cosine of 2x minus 2 sine of x. And that is our derivative. Take the derivative term by term, combine things, use chain rule, and then you're good to go. Make sure when you're doing something like this, do not forget about that chain rule. You have to take the derivative of the outside and the inside as well. You cannot just write cosine of 2x and move on. That would be wrong. You got to have that 2 out in front. That 2 is actually kind of important, all right? So that's all there is to do on that problem. All right, let's look at this example. We have the function f of x is equal to x times e raised to the 2x squared. And we want to find the derivative with respect to x of f of x. Now, this one has a few moving parts. We have this function x right here. And we also have this function e to the 2x squared. So we have one function of x times another function of x. So we have to use the product rule, right? So, if we want to take the derivative of f of x, we have to use the product rule. The product rule is the derivative of the first times the second, 2e to the 2x squared, plus the first times the derivative of the second. Right? Now, for this first term, what's just the derivative of x? Well, it's just 1. So that becomes 1 times e to the 2x squared plus x times the derivative of e to the 2x squared. Now, we have the function e to the function of x. Now, we just have e to the x. The derivative of e to the x is just e to the x, but that's not the case here. We have the derivative of e raised to a function of x, not just x. So we have to use the chain rule, and we're differentiating something like this. Well, the way this works is we get the derivative of e to the f of x is e to that f of x. So it doesn't change. It's still there, just e to the 2x squared. But then we multiply it by the derivative of the exponential function. So it's e to the f of x times the derivative of that f of x. This is the technique you want to use every time when you're differentiating e to some power or e to some function of x. You leave the e to the f of x alone, but then you multiply it by the derivative of that function in the exponent. All right? And now by simplifying, we get this is equal to e to 2x squared plus x times, now what's the derivative of 2x squared? Well, that's just 4x times e to the 2x squared. Well, that's just equal to e to the 2x squared plus 4x squared e to the 2x squared. And then that is our derivative. So this one, a couple moving things. We had to use the product rule because it was two functions multiplied by each other. And then for the derivative of the latter function, we have to use the properties of the exponential function with base e and the chain rule and the derivative of a polynomial. And we do all of that in that middle step right there, and then we just simplify it and we get our answer. All right. Now we have the function f of x is equal to x divided by x squared plus 1 plus x to the 3 halves plus x plus 1. And we want to find the derivative with respect to x of f of x, like we were doing this whole time. So to do this, we take the derivative of each term individually. All right? So the derivative of this function is equal to the derivative of the first term plus the derivative of the second term plus the derivative of the third term plus the derivative of the fourth term. Now, those last three terms aren't too terribly difficult. It's this first guy here that we have to pay the most attention to. So, we want to take the derivative of this guy first. So, I'm going to put that guy right there. Now, notice this is one function divided by another function, or the quotient of two functions. So, what rule do we need to use when we're trying to differentiate the quotient of two functions? The quotient rule. It's almost like it was named that for a reason. Now, quotient rule is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that divided by the bottom squared. So that's it for that term. We'll come back and we'll simplify that in a second. And now we need to take the derivative of the second term. Now, what is the derivative of the second term? Well, that's x to the 3 halves. I know that looks kind of gross, but it's just x to some power. So we have to use the power rule. We pull down the exponent 3 halves times x raised to the 3 halves minus 1 plus the derivative of just x right here. Take the derivative of that guy. That's just plus 1 and then plus 0. That's because the derivative constant is 0. Now we need to simplify. This fraction is x squared plus 1 times the derivative of x, but the derivative of x is just 1 minus x times the derivative of x squared plus 1. Well, that's just 2x. And now we want to divide it by x squared plus 1, it's quantity squared, plus 3/2 x to the 1/2. Why? Because 3/2 minus 1 is 1/2, plus 1. And then one final simplification step. This equal to x squared plus 1 minus 2x squared divided by x squared plus 1 quantity squared plus 3/2 square root of x plus 1. And now you can simplify that x squared minus 2x squared more, but I really don't care in this matter because it's the same answer. And here we have our derivative, and I canceled out my 1 on accident. And then that's our answer. We took the quotient rule of that first term, power rule of the second, rule of x the third term, and then the constant rule on the fourth one. And then the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now in the product rule, it doesn't matter the order you take the derivatives. Quotient rule it does, because we have the subtraction right here. That subtraction means we cannot switch the order of these terms. So make sure you take this derivative correctly. Otherwise, you're going to have a negative out in front that shouldn't be there. All right? So this is how we take the derivative of this function. Alrighty, let's take the derivative of this function. F of x is equal to the square root of x plus 1 over x. Alright, so we want to find d dx of f of x. Well, that's equal to d dx of, now, you could memorize what is the square root of x. You could. Or you can just remember that the square root of x is equal to x to the 1/2. And then we can just do the power rule. And all you have to do is remember to rewrite it in the power rule. You need to know the power rule anyways, so it works out. So we rewrite the square root of x as x to the 1/2 plus, now we have 1 over x. You could do the quotient rule. It will get you the right answer, I promise. It really will. But when you have 1 over x, let's just rewrite that as x to the -1. Just rewrite it as a power, and it'll be a lot easier. So now this derivative is equal to the derivative of x to the 1/2 plus x to the -1. Because we are just adding these two functions together, we can take the derivative term by term. And both of these just require the power rule. What's the derivative of x to the 1/2? Well, it's equal to 1/2 x to the 1/2 minus 1. Pull down the exponent, subtract 1, plus -1 x to the -1 minus 1. Take the exponent, pull it down in front, subtract 1 from the exponent, and that's it. Now notice, just because this was negative does not mean we add 1 or do something else. The fact that it's negative is irrelevant. We're doing the power rule for differentiation. You just pull the exponent down and subtract 1. I don't care if it's negative, positive, 0. I don't care. If it's negative 17 or 17, you pull it down, subtract 1. All right? So this is equal to 1/2 times x to the -1/2 minus x to the -2. Well, that's just equal to 1 over 2 square root x minus 1 over x squared. And that is that derivative. Just take it derivative term by term, rewrite each term in terms of a numeric exponent. So square root becomes 1/2, the reciprocal comes negative, do the power rule for each term, and then simplify it, because I don't like just leaving those negative exponents. And this first one becomes 1 over 2 root x minus 1 over x squared, and then that is your derivative. All right, let's take this derivative. We have f of x is equal to arc sine of x plus pi over 4, and we wish to find the derivative of f of x. And that's just going to be the derivative of arc sine of x plus the derivative of pi over 4. All right? Now, the only way to do this problem is to memorize what is the derivative of arc sine of x, unless you want to go through the representation triangle, use implicit differentiation, solve for dy dx, and go from there. That seems like a massive headache. I advise against it. So, we have dy dx of arc sine of x plus ddx of pi over 4. Now, the derivative with respect to x of arc sine of x is just 1 over the square root of 1 minus x squared. So that term's done, plus the derivative of pi over 4. What is the derivative of pi over 4? Well, that is pi, yes. That is a funny symbol in there, but it just represents a number. It represents the ratio between the circumference and the diameter of a circle. It's pi. It's a fixed number, so it's a constant. And while that looks funny, pi over 4 is still a constant, and so the derivative of it is still just 0. And that gives us our derivative. All right. Given the function f of x is equal to e times the natural log of x plus e, we want to find the derivative with respect to x of f of x. Now, on this one, the trick to this one is to not panic. I know that one looks weird. We got that e out in front times the natural log of something else. It's kind of scary. But do not let this one throw you. We're going to use the chain rule a couple times. But the chain rule is just like peeling back an onion. You just peel it layer by layer. Now, if you try and peel an entire onion in one pull, that's going to be hard. But if you tackle it layer by layer, it's just repeating the same process a couple times. So that's what we're going to do. We're going to do the chain rule a couple of times, and that's it. So this derivative is equal to the derivative of e to the natural log of x plus e. Now, you might be thinking we have to do some kind of product rule here because there's e right here. But remember, e is not the exponential function. E is a number. It is just like pi. It's like 2 square root of 17. It is just a number, right? So we do not have to do the product rule here. You should not do the product rule here, actually, because this is not e to the x. This is just e. It's just a constant. So we can just leave him alone. And now we have to tackle the natural log of x plus e. Well, so this is just the natural log of stuff. So let's just forget about the natural log of x plus e here. We just have the natural log of stuff. So what is the derivative of the natural log of stuff? Well, that's just equal to 1 divided by stuff times the derivative of stuff. That's it. So that's what we're going to do. So this is the derivative of outside natural log right here is equal to 1 over, or don't forget our little e out in front. So we get e times 1 over the natural log of x plus e. All right, but according to this little formula, we also have to tack on the derivative of the stuff. So that's the derivative of the natural log of x plus e. So we take the derivative of the outside layer, and the outside layer is 1 over stuff times the derivative of stuff. But in this case, the stuff is just the natural log of x plus e. So we get e times 1 over the natural log of x plus e times the derivative of the natural log of x plus e. Take the derivative of the outside, that natural log, leave the inside alone, then multiply by the derivative of the inside. This is just equal to e divided by the natural log of x plus e, simplify it, times the derivative of the natural log of x plus e. Well, once again, this is the natural log of stuff. What is the derivative of the natural log of stuff? Well, it's 1 over stuff times the derivative of stuff. Now, we can just go ahead and combine that guy. Now we just have this derivative of x plus e to worry about. Now, what is the derivative of x plus e? Well, the derivative of x is just 1, and the derivative of e is just 0. So this is just times 1. And then we can combine this whole thing to be e divided by the natural log of x plus e times x plus e. And that is the derivative of e times the natural log of x plus e. Let's consider this example. F of x is equal to the natural log of e raised to the x squared plus 1 plus pi over 4, and we wish to find the derivative with respect to x of f of x. Well, that's just equal to the derivative of the natural log of e to the x squared plus 1 plus the derivative with respect to x of pi over 4. All right, so let's tackle this first term, the derivative of the natural log of e to the x squared plus 1. Well, this is the natural log of stuff. And just like we did in the previous problem, we're taking the derivative of the natural log of stuff. That's just equal to the derivative of the outside, evaluated stuff. And what's the derivative of the natural log? It's 1 over the input. So this becomes 1 over e to the x squared plus 1. And now we times the derivative of the inside, just e to the 2, which is equal to e to the x squared plus 1, plus, now what's the derivative of pi over 4? Well, that's just a constant, so that's equal to 0. So we're not done yet. We have this 1 over e to the x squared plus 1 from the natural log, but now we need to multiply it by this derivative. So the derivative of e to the x squared plus 1, well, that's e to some function of x. And when you differentiate e to some function of x, that's just equal to e to that function of x, which is x squared plus 1, times the derivative of that function, x squared plus 1. Now that just becomes 1 over e to the x squared plus 1 times e to the x squared plus 1 times the derivative of x squared plus 1, which is just 2x. Now notice we have a e to the x squared plus 1 divided by e to the x squared plus 1. So those terms are going to be canceled, and we're going to be left with 2x. And that is our answer. We just take the derivative of the natural log of stuff, which is just 1 over stuff, and we multiply that by the derivative of stuff. But in this case, the stuff is the exponential function raised to some function of x. So we have e to the x squared plus 1, we take that derivative, then we just leave that alone, and we multiply it by the derivative of that exponent, which is just x squared plus 1. The derivative of x squared plus 1 becomes 2x, but then these two functions cancel out because of the same thing, and we're left with 2x. Now, that's one way to do this problem. There's another way to do this problem. It is equivalent, but it's a little bit faster. So we have f of x is equal to the natural log of e to the x squared plus 1 plus pi over 4, right? Now, if you remember the properties of exponents, when we have the natural log of e raised to the power, one of the cool things with the natural log is we can pull that power down out in front. So this actually becomes x squared plus 1 times the natural log of e plus pi over 4. And so the derivative with respect to x of f of x, that was a horrible, horrible thing, is equal to the derivative of x squared plus 1 times the natural log of e. But what is the natural log of e? Well, one of the things you should memorize by now is the natural log of e is just 1. So this is equal to the derivative of x squared plus 1 times, or plus the derivative of pi over 4. And what's the derivative of x squared plus 1? That's just 2x. Derivative of pi over 4, well, that's just 0. So that derivative is equal to 2x. So there are two ways to do this problem. One's a little bit harder, but it doesn't require you to remember any of the fun properties about the natural log. You remember the properties about the natural log, you can do some manipulation up front, take the derivative, and get your answer. Otherwise, you're stuck going through this mess. Either way, you get to the same answer. All right, now let's consider this function f of x is equal to tangent of x plus x squared plus 1, and we wish to find the derivative with respect to x of f of x. Well, that's just equal to the derivative of these three things term by term. So the first up, you need to take the derivative of tangent of x. What is the tangent of x? Well, that's just equal to secant squared of x. You could memorize the formula, or you can rewrite tangent as sine over cosine, do the quotient rule, simplify, get the same answer. So this is equal to secant squared of x plus the derivative of x squared. Well, what is the derivative of x squared? Well, the derivative of x squared is just 2x. Just a simple application of the power rule. Pull down the exponent, subtract 1, and then plus the derivative of 1, which is just 0. So this derivative is just secant squared of x plus 2x. And then there we have our derivative. Now, that's enough for that problem. Let's look at the next one. And because I didn't think to put pause, you get to see me write this one down. So you get 12 is going to be f of x is equal to 2 cosine of x sine of x. So this is what we want to differentiate, 2 cosine of x sine of x. Well, the derivative with respect to x of f of x is equal to 2 times, I'm just going to pull the 2 out in front because I don't care about it, 2 times the first times the derivative of the second plus the derivative of the first times the second. And now we're just going to simplify. Now we're going to evaluate these individual derivatives. Equal to 2 times cosine of x times the derivative of sine of x. Well, that's just cosine of x. Now plus the derivative of cosine of x. Well, that's just negative sine of x times sine of x. Well, this is just equal to 2 times cosine squared of x minus sine squared of x. All right, so we have, that is our derivative. But does anybody recognize what cosine squared x minus sine squared of x is? We know sine squared of x plus cosine squared of x is equal to 1. But what is cosine squared of x minus sine squared of x? Well, that's just equal to 2 times, now cosine squared of x minus sine squared of x is actually equal to cosine of 2x. So this whole thing is equal to 2 cosine of 2x. And then that is our answer. Now I'd like to point out you can stop here. So this is just simplification step, but you can stop at 2 cosine squared x minus sine squared x. And then that is how we just take the derivative of that function. All right, so that's enough of normal differentiation or explicit differentiation. Now let's go over a few practice problems on implicit differentiation, i.e. differentiating equations in terms of x and y rather than differentiating functions in terms of x. So for example, we could have the function f of x is equal to x squared plus 17, or we could have a situation where we have, say, x plus y is equal to 7. Now, we know how to differentiate that guy. That's no problem. But at these guys, x plus y is equal to 7. So we're just going to go over implicit differentiation techniques. If you want to see a more comprehensive analysis of implicit differentiation, please go watch please go study the material from section 3.6 on implicit differentiation. In fact, I'm pretty sure that was the second to last section that we managed to cover before this whole coronavirus breakout. So go review your notes from that if you want a more detailed explanation. Otherwise, I'm just going to go through 3 or 4 practice problems. All right. So let's just get straight into this. First, let's give in x plus y is equal to 12. And I just wrote z, 1z. Cool. Is equal to 12. Find dy dx. Well, we know x plus y is equal to 12. But now what we need to do is differentiate everything with respect to x. So we take d dx of x plus y, and that's equal to d dx of 12. And then take this derivative, we pass it each term, so that's d dx of x plus d dx of y is equal to, now what is the derivative of 12? Well, it doesn't matter what you're differentiating in respect to. The derivative constant is always 0. So now we can tackle these terms term by term. What is the derivative of x with respect to x? Well, that's just equal to 1. Plus, now the derivative with respect to x of y, well, that is just dy dx, and this is all equal to 0. So that tells us that dy over dx is equal to negative 1. Just take the derivative with respect to x at both sides. The derivative of x is just 1, but the derivative of y is dy dx, and then just solve for dy dx, and we get dy dx is equal to negative 1. But now let's see something a little more intense. What about, say, x squared plus y squared is equal to 4? How would we differentiate that? So suppose we've given that function and we want to find dy dx. All right? So we take d dx of both sides. And then, well, let's just go ahead and knock out this right-hand side. What is this going to be equal to? That's just the derivative constant. That's going to be equal to 0. So, now for here, we take the derivative with respect to x of both terms. So we get the derivative of x squared plus the derivative of y squared is equal to 0. Now, the derivative of x squared, that's the exact same way we'd always do it. That's just going to be 2x, right? Now, what about the derivative of y squared? Well, the derivative of y squared, y is a function of x, so we have to use the chain rule. So we kind of take the derivative of the outside, leave the inside alone, then take the derivative of the inside. And right here, the outside is y, and we have squared it. So when we differentiate it, we just got to use the power rule. So that's just equal to 2y. Just pull down the exponent, subtract 1. We just get 2y. But then we have to tack on a d dx of y. But what is d dx of y? That's just dy dx. That's equal to 0. And then so that tells us that dy over dx is equal to negative x over y. A simple way to remember how to do simplistic differentiation. Wow, that messed that up. The derivative of y squared, take the derivative exactly like you would with x and just tack on a dy dx at the end. That's how you do the simplistic differentiation. Differentiate the y function in terms of x the exact same way you would do it if it was an x, but then just multiply it by dy dx at the end. All right, given this problem, 2x squared y plus 3x is equal to y, and we want to find dy dx. All right, so when we want to do this, we just take the derivative with respect to x of both sides. Let's do it squared y plus 3x is equal to d dx of y. Well, that's just d dx of 2x squared y plus d dx 3x is equal to, now what is d dx of y? Well, the derivative with respect to x of y is just dy over the dx, right? So we just leave that alone. Now, the derivative with respect to x of 2x squared y. That means we have two functions in there multiplied by each other, or the product of x and y. So we have to use the product rule here. But what I'm going to go ahead and do is pull this 2 out in front. So we're just taking the derivative with respect to x of x squared y. Now, y is a function of x. That's what we're assuming. So when we take the derivative, it's just like taking the derivative of a function of x. That's it. You just got to use the chain rule in there. But you got to make sure you do the product rule here. Y is a function of x. So we have x squared times a function of x. So a product of functions of x, so the product rule. So this is equal to 2 times the derivative of the first times the second plus the first times the derivative of the second. And so that's it. Derivative first times the second plus the first times the derivative of the second plus d dx of 3x. Well, what's the derivative of 3x? That's just equal to 3. And that's all equal to dy over dx. And then we get 2 times, now what's the derivative of x squared? Well, that's just 2x, and we're multiplying that by y, plus x squared times the derivative with respect to x of y. Well, that's just dy over dx plus 3 is equal to dy over dx. Now here, we can simplify this into 4xy plus 2x squared dy over dx plus 3 is equal to dy over dx. Now we just have to solve for dy dx. So what we're going to do is move this dy dx over and then all the other terms over to the right hand side. So we get 2x squared dy over dx minus dy over dx is equal to negative times 4xy plus 3. That's just because I took this 4xy and this 3 and moved them over to the right hand side, and I took this dy dx and moved over to the left hand side. So essentially, move everything that has a dy dx term in it to the left, everything else over to the right. And here's why. Now this dy dx is in all the terms. What just happened? My bad. So we can pull the dy dx out in front. 2x squared minus 1 is equal to negative 4xy plus 3. Now, we have dy dx times something equal to something else. Divide both sides by the 2x squared minus 1. So we have dy over dx is equal to negative 4xy plus 3 divided by 2x squared minus 1. And so that is dy dx. So when you're doing implicit differentiation, differentiate y the exact same way you would x, and then tack on a dy dx at the end. And be careful when you have the product of x and y, because you might have to use a product rule, quotient rule, or a chain rule. All right? Okay. If you want to see more examples on implicit differentiation, please go review the notes from section 3.6. If you have any questions about implicit differentiation or explicit differentiation, please don't hesitate to let me know. And once again, I'd like to point out, these are just some examples. These are not the possible choices for the final exam. A final exam will consist of different problems. However, techniques for these kinds of problems will remain the same. But make sure you study your techniques, your rules, and the fun properties that we have with derivatives, along with all the other theory we have related to derivatives from chapter 3. All of those fun formulas, finding tangent lines, finding slopes of tangent lines, things like that. So, if you have any questions about any of this material, please do not hesitate to let me know. All right, guys, I'll see you next time, where we will have more fun with math.